Alrighty, let's get started. Hello, everybody, and welcome to another ASTRO 3D ECR Astronomers in Australia seminar series. My name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia, which is part of the International Centre for Radio Astronomy Research. My co-chair today is Dr. Geoffrey Simpson, who is a postdoc at the University of New South Wales. Now, before we begin today, it's important for us to acknowledge the traditional custodians of the land on which we're meeting. So the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. Myself and our two speakers today are joining you from the land of the Whadjuk Noongar people, and my co-chair Geoffrey is joining us from the land of the Watamatagal clan of the Darug Nation. We pay our respects to their elders past and present and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by ASTRO 3D, which is the ARC Centre of Excellence for all sky astrophysics in 3 dimensions. Basically, COVID-19 has affected our ability to travel and present at international seminars. And for us here in Australia, it's quite difficult because the time zones mean that often meetings take place at 2 or 3 a.m. in the morning for us. So this lack of opportunity to network could disadvantage junior astronomers when they're going to enter the job market. So this series aims to combat these issues by providing them a platform to present their work to the world. So we've got 2 talks this hour. Each talk will be 20 minutes in length with 5 minutes for questions at the end of each talk. So please save your questions until the end, and you can either pop them in the chat function or just raise your hand. These talks are also being recorded, and they're going to be placed afterwards on the ASTRO 3D YouTube channel. So by being here today, you're agreeing to abide by ASTRO 3D's meeting code of conduct. Okay, well, let's move on to our second speaker for today. Our second speaker is Dr. Lilian Garratt-Smithson, who is a postdoc also at ICRAR UWA. So the title of Lilian's talk is Real or Not Real? What simulations can and cannot tell us about cold and cool phases of the CGM? So you can go ahead and share them.
Oh, great, thanks, Amelia. So yeah, thanks very much for the opportunity to give this talk. And I think it nicely actually follows on from what Garima was talking about, particularly initially with the scatter and the H1 halo mass relation. So this is work I've been doing as a research associate at the UWA as part of ASTRO 3D. And I'm really going to be focusing more on kind of hydrodynamical simulations and kind of coming from that point of view. So when I started my postdoc, I was given this task of connecting simulations to the ASCAP Flash survey. So really, Flash is a H1 absorption survey. It's a blind survey, so it's across the whole southern sky. It's got 150,000 sight lines, and it's interested in this kind of a H1 absorption event. So this is a spin flip in the 21 centimeter spin flip for the electron and hydrogen. And what's quite interesting about Flash, so it's a blind survey, so it's going to get a lot of, so obviously there are a lot of galaxies being intersected. And what's interesting about it is you could imagine you could be getting an absorption event either from, say, a host galaxy itself. So your source will typically be kind of a quasar, this kind of continuum radio source. And or it could be an intervening galaxy, and how do we tell just from a single absorption event? So I think this is where simulations could be really useful. And the interesting thing about Flash is that it's really sensitive to the coldest atomic hydrogen in a galaxy. So here we've got the cumulative number count of absorption detections as a function of the column density, and you can see that vertical line there is DLA column density. So when I say DLA, I simply mean very high density H1, and you can see it's both a steep function of temperature, so the spin temperature, you're really sensitive to the coldest of this H1, and also really dense, so above 10 to the 20.5 centimeter squared. So initially, we thought the first thing to do is a blind survey. We need a lot of galaxies to connect with something large scale like this. we'll try Eagle simulations. So it's this cosmological scale simulation. I'll talk about it in a sec. And we thought, why don't we look at this distribution of this really dense, cold H1 in out to the redshift of interest. So Flash will be interested between 0.4 and 1. So we went out to 2 just to kind of see what was going on. So for those of you who aren't familiar with Eagle, so this is a cosmological scale hydrodynamical simulation. And we were particularly used the kind of 25 megaparsec box, so this big volume of the universe, and it's calibrated to produce the galaxy stellar mass function, galaxy stellar mass size relation, and the black hole stellar mass relation. So when I say calibrated, I mean kind of the subgrid physics, things like AGN feedback, stellar feedback, will have been calibrated to produce something sensible at redshift 0. But what's not calibrated is the detailed kind of gas physics. So you can see, you know, the cold gas here has not been calibrated, so we can consider those more or less predictions. However, I say cold gas, Eagle tends to go down to around, well, it does go down to around 8,000 Kelvin. This is because an artificial equation of state has been imposed just to avoid numerical fragmentation, basically going below the resolution of the simulation. And you can see that on the right there, you've got a temperature versus density plot. And you can see it's the, I don't know if you can see my cursor, but in the lower right corner, you can kind of see this, this artificial equation of state there. So you can see things are kind of heated. It keeps things warm, basically, the ISM warm. So obviously we needed to post-process the simulation. We need to say, how can we needed to, take these kind of, perhaps these gas particles around this kind of equation of state and say how much H1 we think is there, how much molecular hydrogen. This has been done before, it's been pretty well documented. If you're interested, you can look at things like Claudia Lagos's paper in 2015, and they obtained pretty good kind of global relations, H1 global relations. So I won't go into that too much. If you're interested in that post-processing method, you can look at my 2021 paper. And so what we did, we took the outputs of the simulation, and then we were quite interested in the covering fractions of this H1. So when I say covering fractions, I mean, so if you concentrate on the top plots there, this is if you take a galaxy, rotate it kind of face on, and look and grid it so you can get the column density of H1. And the covering fraction is the particularly covering fraction of DLAs is the fraction of that area that has can be attributed to gas with column densities above 10 to the 20.5. So it's that how much of that kind of area is that kind of dense gas. And so that's what we've done at the top there. So it's an example of us doing this. We've gridded them, and then we've found the column densities, and then found this kind of function. You can see, and the grid, the size of the grid was set by the virial radii of the galaxy. And on the bottom there, we also used a method that was defined in this Mitchell 2019 paper to try and say something about which gas is ISM, interstellar medium, which gas is CGM, because obviously it's not completely obvious. One of the things we looked for was kind of rotational support to be in the ISM. So you can imagine kind of the galactic disk, where we're really looking at that gas. So you can see it's been applied there, and you've got this in the blue, the non-star forming ISM, and in the yellow, the star forming ISM. And you can see that's heavily a function of like of whether there's a gas disk there or not. You can see them. So I'll just a few key results from this work was that we found the covering fraction was a steep function of redshift, and how the covering fraction varies with virial radius of a halo depends very much on redshift. So what this was telling us was at kind of higher redshift, you're getting a significant portion of that virial radius is has some kind of high column density gas in it. So what this might mean, and what we looked at later was next, was that maybe perhaps there's more H1 in the CGM than perhaps we thought. So here we've got H1 mass and stellar mass, and we've got the amount of H1 mass that you've calculated if you just use a friends-to-friends algorithm subfind, if you just look at the H1 in the ISM, and if you look in a 70 kiloparsec aperture. for galaxies. And here you can see that yellow, especially at redshift 0, the difference between the yellow line and the pink line is quite pronounced at higher stellar masses. You can see at higher stellar mass, there's a significant amount of H1 in the CGM. So this led us to our next question. So how robust is that result? And in particular, what can we say about the cold phase of the CGM? What can we use simulations? How can we use simulations for that? So why is this interesting? I mean, the CGM is interesting in of itself because it holds answers to some of the key questions in galaxy evolution. So how do galaxies sustain star formation? How galaxies are quenched? Where are the missing baryons? And where is the enriched material generated by stars? So it's quite interesting. Erin, I've got this lovely diagram on the right there from Tumlinson et al. 2017, just showing some of the processes that are affecting the gas in the CGM. But however, it's so cosmological hydrodynamical simulations are able to reproduce a wide variety of galaxy properties, but it's currently kind of well known now that they typically cannot resolve the CGM. It's typically under-resolved. And this is because hydrodynamical simulations typically have a resolution that follows the mass. So obviously the centers of the galaxy is going to be quite well resolved, but the outskirts are not. And here on the right, they've got an example. Fricke van der Voort increased the resolution in the CGM of a galaxy. And if you focus on the bottom there, the bottom 3 plots, this is colored by column density, and you can see the amount of high column density H1 vary significantly by just changing the resolution of a simulation. So we're very much not on we still don't have the resolution to resolve the CGM. And we also know that the CGM is highly dependent on physical processes modelled and how this is done. So I've got an example from my 2019 paper here. And on the left there, I've got type 2 supernovae, stellar winds, and high mass X-ray binary feedback going off in a dwarf galaxy. And on the right there, I've got just type 2 supernovae. And just simply from changing the stellar feedback prescriptions, you can see that's had a huge impact on the kind of densities. So you've got it's coloured by density. And if you look at the temperatures, this is zooming out of it, you can see the outskirts of the galaxy as being quite heavily impacted on just simply what kind of stellar feedback events have been modelled. This kind of result was only I was only able to get this by modelling individual stellar feedback events, so individual supernovae, individual high mass X-ray binaries. And you can see on the left there, we ended up with this kind of chimney formation where you end up with this kind of diffuse hot gas being jettisoned out to higher radii. So that led us to our third question, which is how do different evolutionary processes impact the gas in the CGM and ISM, and can we break some of the degeneracy seen in cosmological simulations? So this led me to set up a set of cosmological zoom-in simulations. So I won't go too much heavily into the detail. If you're interested, I can answer questions on this. So we're using our in-house version of Gadget 3, and some of the key features are here. So it uses this SPHS algorithm, which basically means it can follow converging flows, which is obviously very important when you're kind of trying to model feedback. You have a lot of converging kind of shocks. Also, you have a modular subgrid physics recipes. So for example, we could have the illustrious TNG star formation scheme with the Eagle stellar feedback prescription. So we can really try and break some of that degeneracy that we see between subgrid physics recipes. We use the chemistry and cooling library Grackle to follow H1 formation and molecular hydrogen formation as well. And we also use this CELIB, which calculates the chemical and energetic yields from stellar populations. So here again, we've gone back from that individual stars. We can do an idealized simulation, and we've had to do kind of stellar populations and individual particles. And we've also got a stochastic black hole seeding scheme based on Taylor et al. And our high res runs, which is still running because I can't show you, I'm just showing you some preliminary results. But our high-res runs are comparable to the Eagle high-resolution run. So we'll be able to kind of check the degeneracy between different subgrid models at that scale. And all this was run using Pawsey supercomputing time as well, I should say. So I'm going to show you a few of the preliminary results, particularly from the dark matter only run. So how I set up the ICs is I use a Planck 2018 cosmology, and they're set up using a co-coordinatic And I'll talk a little bit about that in a sec. So, and what happens is I grab my galaxy, I zoom in, I increase the resolution of particles within, by a mass factor of 8, within a 4 virial radii of that halo. And then I actually subsample the remaining gas kind of outside that by a factor of 8. So it just helps computationally to do that. It takes less time. And genetics really cool actually, because it can modify initial conditions. So the idea is you can do these kind of genetic modifications, they call them. So this is where you change the overdensity of the, and make tweaks to the overdensity within that 4 kind of virial radii that close to the galaxy. However, keep the large scale structure very similar. So in that way, you can really tweak these mass accretion histories of individual halos. So if you're interested in that and the whole process, I've got this data. Recently it's been used in the Davies et al. Paper 2021. So I'd encourage you to look there. And so what I mean by this is, so I can take, what I can do is say at redshift 4, I want the halo to have be less dense, the dark matter particles be less dense surrounding that halo at redshift 4, but I want the same halo mass at redshift 2. So basically what I'm doing there is I'm delaying the formation of that halo. So at the top there, this is where I've modified the overdensity by a factor of 0.8 at redshift 4.5. And then at redshift 2, the right column is redshift 2. And on the bottom there, I've increased the overdensity by 1.2 at redshift 4. And then you can see at redshift 2, it's looking relatively similar. So what I've done there is I've delayed the formation in the first case. And you can see that here I've got just XY plots of the dark matter particles, and the virial radii of halos are shown with those circles. This is yeah, that's what those circles are, in case you're wondering. So you can see cool, great, thanks, Amelia. So yeah, you can see there's quite a lot more substructure in that lower case there, and you see already, and you can see there's a lot less dense in the kind of uppercase. So I've got a few examples. So this is the mass accretion history of those two. So on the orange one is the one that was denser at redshift 4, and then the blue one is the one that was less dense. This is less low over density. So you can see there that by redshift 1, actually the masses have converged. This is halo mass versus redshift. And so yeah, right by redshift 1, which is that red dash line, they've converged. And you can see they're a lot more similar at redshift 2. They're not quite the same, but they are similar. But you can see at redshift 4, they're quite different, the halo mass. So it's really affected kind of that mass accretion history of those two galaxies. And so one cool thing that I'm going to be I found I can do with this is, obviously I can tweak, by tweaking the formation history of the halo, I can really kind of think about how the angular momentum of that dark matter is built up. So this is what I've done here. I've got the specific angular momentum of dark matter versus redshift. And then I've got the dashed line, just so the two is redshift 4 on the right and redshift 2 on the left. And you can see at redshift 4, they've got quite different, this is the specific angular momentum within the virial radii. They're quite different at redshift 4, and they're quite similar at redshift 2. But you can also see there's something quite interesting happening at redshift 0, which I want to investigate further. So you're getting quite the divergent histories beyond redshift 2, which is quite interesting. So I'm really interested in the gas morphology. So these are still running. So I've just shown you at these two redshift. But you can see already that there's seems to be differences in the gas morphology. You've got quite an ordered disk at the top there, and a slightly more disordered disk on the bottom there. So I'm guessing this is something to do with the feedback that's going on. And the runs that are currently running, I've changed the stellar feedback. I put 8 types of stellar feedback that I've included, and the AGN feedback as well. So we heard from Green's talk how important AGN is. So I think that'll be quite interesting once those results are in. And the other thing we've put in is we've put flags that can track the cold gas in the simulation. So we really want to know what's happening to the cold gas. Is it forming stars? Is it getting ejected out of the CGM? And so here I've got these are actually results from idealized simulations of a galaxy of a similar mass. And what I've done is I've tracked any gas that's been above a certain density threshold and below a certain temperature threshold, and or has been a part of the equation, Eagle equation of state, that equation of state I showed you to start with. And you can see that if you look at the top left there, you've got the amount of the mass. This is the mass that has ever been kind of in that cold state, divided by the total initial mass of this initial gas mass of this galaxy. And you can see obviously it increases. You can see most of it is enriched by kind of this 0.6 gigayear into the idealized simulation. And you can do things like follow how much of it's outside 10 kiloparsec, how much of it forms stars. And on the bottom there, I thought this was a nice illustration of how we can really start to disentangle what's going on. So this is the density histograms. So this is the mass in different density bins, or different of any gas that's been cold at some point during the simulation, cold and dense, and then how that varies throughout the simulation. So we can track what's going on and where its end state is. So that'll be quite cool when those results come through from the Zoom simulations. So where to next? So we really want to know, is there a key evolutionary process that determines the properties of the cold gas in a galaxy? For example, does the mass accretion history of the halo have a bigger impact on the cold gas covering fractions than the AGM feedback? So how does the halo mass impact this interplay? So we've actually got two sets of cosmological zooms being run currently. You saw some of the Milky Way kind of actually it's slightly below Milky Way size mass, but we have Milky Way size mass, high res ones, and dwarf mass galaxies. And does the key evolutionary processes involved, does that change with halo mass? And also, we're quite interested in this build-up of angular momentum. So genetic offers a way of explicitly investigating the link between the halo mass accretion history and the build-up of momentum within the galaxy. So I think that'll be quite particularly, and also the interplay between the dark matter and kind of the H1 angular momentum too will be quite an interesting result going forward. So thank you. You got any questions?
Thank you very much, Lilian. Fantastic talk. So I'll hand over to Jeffrey for question time.
Thank you, Lilian. Do we have questions? I'm sure there was that thing where it was diverging at redshift of 0. Do you have any thoughts about what was going on there?
No, I'm quite curious about this. This is all pretty new. So I'm going to investigate. I'm guessing maybe a merger. It's also, so I should say as well, I get slightly different results. I'm analysing my galaxies or halos using Velociraptor, Halo Finder, and they've got different versions of the virial mass. So maybe if I change it, it did seem like it was consistent across all of them. So I think maybe a merger event, but it's interesting it doesn't happen in the other one. So yeah, I'm interested in that. What's happening? That will be interesting to see.
So actually, I had a follow-on question from that. Maybe I can jump in. In terms of the build-up of the angular momentum plots, I think it was your slide 20, and the difference between the two. Do you have a feeling for which is probably more correct of the two? Or more likely to follow the observations?
No, so not really. So this isn't, it's kind of more, I think the simulations I'm running currently are more of a parameter kind of study. They're not, so they could be, these in effect are different galaxies now. It's just, I'm really trying to disentangle what impact like a delayed formation would have on, say, the gas in the galaxy, the cold gas in the galaxy, the angular momentum in the galaxy. So I wouldn't say either of them is more correct than another. It depends on your galaxy, but I think it's quite interesting to take, like, it's more like an experiment. I've taken that galaxy and I've said, okay, let's tweak the halo mass accretion history, or so I could really kind of disentangle some of those effects. That's kind of the idea of it.
Okay,
if that makes sense.
No, it does. So are you planning on comparing this to more of these higher redshift IFS surveys that are coming out, like Magpie, KMOS, these sorts of things, so you can get further back in redshift and start comparing the angular momentum build-up?
That would be cool. Yeah, this is all very new to me, the angular momentum. This is something I'm going to be working on the next 3 months. So yes, that would be really cool to do. I'd have to, yeah.
Speak to the observers.
Talk to you about it. Yeah, speak to the observers.
Thanks, Lilian.
Okay, we've got a question from Hamza.
Yeah, very quick question actually. So thanks for the really interesting talk. There was there was research, if I remember correctly, a while ago on how this angular momentum, I don't know if you already covered this, correlates with the color. So for example, blue being spiral is more correlated with higher angular momentum, and some, it's, they found a little bit of correlation, but I'm not sure if it was significant. So do you consider that at all?
That again, that'll be a really cool thing to do, actually. Yeah, I've seen Eagle. I've seen results in Eagle doing that, looking at kind of color. I'd have to, yeah, I think that could be something quite a nice thing to look at, particularly, yeah, looking at the when I have these, I do have stellar disks, so I could maybe look at that, looking at the angular momentum in the stellar disk.
Right. The previous one was Pappus Tergis, if I remember correctly. Those were the papers. I remember there's probably more on that in the subsequent work. Yeah.
Oh, great. Thank you. Yeah, that's really interesting.
Sure.
Okay, any other questions? If not, we can hand back to Amelia.
Great. Thanks, Jeffrey. So I'd like to thank both of our speakers in this session, Lilian and Garima, for 2 fantastic talks. And thank you very much, audience, for listening.